The purpose of gears is torque transmission or power transmission. The purpose is to increase torque while decreasing speed, like from a motor. But what we do here in Designatronics is we specialize in doing this very accurately. Special attention must be given to the center distance in the mesh and in the housing itself. This is one of the topics that we'll touch the most during this presentation. Again, if you see the diagram here, the center distance and the pitch diameter, working with those two things will result in good function or bad function of your mechanism. Next slide. So the first type of gear that we want to talk about is the spur gear. The spur gear is the simplest to manufacture, and it's capable of achieving the highest AGMA quality. In our facilities, we can achieve an AGMA quality of 14, which is very high. It's the easiest to control the tooth thickness for and the face surface variation. It also has the simplest calculations. It has no thrust loads, and all forces are used in rotation. Again, as we mentioned before, a common error is not to increase the housing center distance to allow for rotational error. If you look at the diagram, if you look at the tooth thickness in the middle of the tooth, working with this to increase or decrease the backlash in a mesh, which is two gears together, will determine how accurate your mechanism will be, and it will also determine what kind of center distance you need and what you will need to do to modify an addendum in case there might be interference. We'll talk about that later. Next slide. So the movement is possible due to the involute surface profile. If you look at the diagram above, the left-hand involute trace and the right-hand involute trace will generate the tooth shape. This is what allows for rotation. Cycloidal teeth is a different type of profile, one used in clock gears. We won't cover this in this presentation, but the involute profile that we talk about here is the best to transmit torque accurately. Next slide. Another type of gear that we want to talk about is the helical gear. Helical gears are more complex to manufacture as they require the teeth to be cut at an angle to the axis of rotation. A right-hand pair and left-hand pair must be used together in one mesh. The helix angle does allow for better mesh, less noise, and more torque transmission. But a drawback is that it has the added thrust loads included. These thrust loads will require thrust bearings or angular contact bearings to be included in the mechanism. We have a division called QBC, which can help source bearings. In any project, sourcing the bearings can be a hurdle, but we can do so very quickly, especially if they need modifications or any other customizations to the bearings. As you can see on the diagram above, the helix angle is simply the angle between the bore axis and the line tangent to the tooth above. You will see a helix angle also used in a worm mesh. I have a sample here. Not sure if you guys can see. I have a sample here of a gear cut with that helix angle. So another type of gear that we want to talk about is the internal gear. So internal gears require very accurate outside diameters or banking surfaces to manufacture and assembly. If your internal gear is already incorporated into your housing, you don't really have to worry about that. But if it's not, you're going to need very accurate surfaces. And I'm talking about 2/10 and very concentric, about 5/10. 0.0005 of an inch of accuracy on that run out. Here's an example of an internal gear, but one that's already incorporated into the housing. This particular housing has 3 internal gears already incorporated into the design. And this was done by shaping, a manufacturing method which we will talk about later. This side was done first, followed by this internal side with a different shaper, flipped over and shaped for the 3rd internal gear.
Mhm.
Another type of gear that require very accurate machining methods is the spur rack. The spur rack requires a very accurate straightness at the base because special attention has to be given to the entire length of the part, because tolerance adds up inch per inch or millimeter per millimeter. An example of this, say you're trying to make an AGMA 10 spur rack. An example call out for the base is 2/10 of inch to inch straightness. At 10 inches, this can amount to 0.002 inches of height variation, which can cause interference with the mating gear, meaning it won't let the mating gear rotate. One way to go around this and make it work is to either straighten the spur rack over the length, or cut it piece by piece, but make holes that are very accurate to the teeth of the gear. That's something that we specialize in, so that as you assemble this spur rack into your assembly, the spur rack bends itself as assembled, and that accuracy is maintained. The last gear that we want to talk about in this slide is the helical rack. The helical rack incorporates everything we spoke about previously. It has the helix angle or the helical angle on the spur rack. This helps for, again, making a quiet mesh and a stronger one, but it does have those added truss loads. Next slide. Bevel gears is another type of gear that we want to talk about. Bevel gears can help change the axis of rotation to various angles, the most common one being 90 degrees. One thing with bevel gears is that they require finding a pitch apex to back when mounting. If you look at the diagram, the pitch apex is that imaginary point in between both bevel gears. When this is found, smooth motion or your calculated maximum error is achieved. We suggest an accurate banking step or wall to contact the back of the bevel gear to find that pitch apex to back. An alternative, which a lot of our customers do, is to clamp or temporarily attach the bevel gear, find the proper backlash or function, and then drill and pin or use another type of permanent attachment. A lot of customers use our spray lock in those bevel gears, and once it's tight, it doesn't go anywhere. So not only can you adjust and find that location, but once you tighten it, it's not going anywhere and can be used for servicing. We'll talk about the spray lock a little later. Here's a sample of a bevel gear that we have and what it looks like. This one has a keyway, which we'll talk about later. But again, finding the location of that pitch apex to back is the most important thing for these. Next slide. So we have all different types of bevel gears. The spiral bevel gear is very good in that it allows for a very quiet mesh and also allows for high torque transmission, even more than a regular bevel gear. We do offer these as a standard item in our website. One thing is a lot of customers want to modify the standards, and that's fine, but these are very hard. A lot of customers have issues when buying these, either with one machining the parts themselves because they tend to be so hard, or after, if they can machine them, maintaining the accuracy is very tough. So that's something that we here in Designatronics can do very well. We have special methods that use diamond cutted tooling to make modifications to these parts. We can do this as a service, no problem. So if you are looking at a bevel gear like this and need modifications, it's best to give it to us because we know how to work these and know how to maintain the accuracy, which is essential for your mesh. Next slide. Another type of gear is the worm and worm gear set. So it allows for a large ratio in a small amount of space. You need very precise axial alignments and very accurate housing locations. This particular item is the one we find customers having the most issues with, especially for accuracy situations or precise situations, because you have to find the center distance very accurately in two different axes. Again, these do allow for a large ratio in a small space. You do need a soft gear and a hard gear combination. Some customers want both to be hard, but that's tough. Dry foam lubrication is an option to decrease wear and increase efficiency, since efficiency is a problem sometimes with these gears, as there's a lot of sliding friction encountered with them. Next slide. So here's a sample. Here's a sample worm gear. Let's say this is the worm. So not only do you have to find the center distance in, let's say, the Y direction when assembling, but you also have to find it in the X direction, which allows for more error. A lot of customers will buy very accurate worm and worm gear sets, expecting things to work very well, but when assembling, they tend to bind. And usually that binding occurs because this center distances were not incorporated into the housing already. So one can find the accuracy in the gears themselves and play with the tooth thickness. But if you don't have the accuracy in the housing itself has to be even more accurate than the gears to find that a sweet spot where the gears will work and mesh the best. So we do offer worm and worm gear sets off the shelf. You simply have to change the part number. The example you can see here, you can change the bore size by changing one of these digits or changing the code for single, double, or quadruple threads. And you can have very high ratios because the worm counts as one tooth, let's say, and no matter how many teeth you have on the mating worm gear, that's the ratio you have. So let's say you have 60 to 1, or if you have a double thread, you'll have a 60 to 2 ratio on these. And the higher the number of threads, the faster the gear will spin. A lot of customers look for this for the no backdrive properties of worm and worm gear sets, and that's when they lock together. That can be found in the single threaded worms combination, but you won't find it in a double or quadruple thread. So if you are looking for the zero backdrive or locking assembly, you want to do so with a single threaded only. And even though the theory will say it'll lock, you have to make sure you do a trial and error and have proof depending on the loads you have in your assembly. Next slide. So we're gonna get into detail with the teeth themselves, because when you're generating a mesh, a lot of interesting things tend to happen. There's a lot of problems with interference and contact ratio. Those are the first things you want to look at when making a mesh. Once you figure out the ratio that you need and you decide what type of gear mechanism you'll have, the first things you have to do is check the interference and the contact ratio. And we'll mention those two things. A quick way to know if you'll have interference is if the tip of any of these teeth touch below the base circle of the gear. We can help with determining if that will happen. We have special software that can do it. There's also calculations possible, but a rule of thumb is anytime you mesh two gears together and you see this tip going anywhere in this base circle or interacting with this base circle, you'll have interference. So just as a general summary, the diametral pitch denotes the tooth size. So if you hear about that, that's just the tooth size. The module is the equivalent in metric. You do have different pressure angles, which is just the angle of the involute profile. 20° gives the best balance for sliding, interference, and forces involved. 25° is harder to manufacture, but is quieter and smoother and has a higher chance of tooth interference at the root. 14.5 is not as smooth. It is noisy. It can be cheap to manufacture, but is not used as often anymore. Next slide. So again, I mentioned contact ratio. So once you find that your teeth don't have interference or you're not going below that base circle, you have to look at the contact ratio. So the contact ratio cannot be less than 1.2. If you have a contact ratio less than 1.2, that means you only have one tooth in mesh all the time. What that means is that you'll have a gap and you'll lose motion due to the backlash between the teeth. So what you want to have is 1.2, which means that as the first tooth is coming out of the mesh, the second tooth is already coming in and it's already in contact. So you always want to have two teeth in mesh, and 1.2 is the number you want to achieve. Backlash can increase with the center distance. And like I mentioned before, that's built into the housing itself. So you can control center distance in the housing itself and in the gear mesh theoretically. But in reality, the backlash can increase with both the center distance in the housing and in the actual tooth of the gear. So one you can control outside and one you can control inside your gear mesh. Next slide. So you do need a minimum backlash for sliding to occur and rotation to begin. No backlash, as you can see in the diagram above with A. No backlash means that the teeth will have nowhere to go and the forces will go into jamming the gears against each other instead of rotating. So they'll push against each other and they won't rotate. With a small amount of backlash, as in diagram B, there's space created. So when motion and when one gear turns, it will have a place to go and it'll allow for a push and the rolling action between the gear teeth, and both gears will mesh and turn. We do offer anti-backlash gears, which produce zero backlash. It's a special design where gear teeth are spring-loaded, so the gap is closed, but motion still occurs. This motion occurs due to the process in the springs. I have a sample here of an anti-backlash gear. The anti-backlash gear is loaded, preloaded like this. You can see how the springs stretch. This is inserted into the mechanism, and it'll allow for motion with zero backlash. Now, one of the drawbacks to this is that the total torque you can transmit will be limited by the torque of the springs themselves. So you won't use the full strength of the gear tooth. This will be a limiting factor for torque transmission. The good thing is for anti-backlash gears, most of the time, you just want them to be accurate and you'll have a low torque application. So this type of gear will work. Next slide. So if you're designing, a quick and dirty calculation would be to use the Lewis formula to calculate the bending strength. So you can use 1/3 of the ultimate tensile strength of any material in this calculation. And then the rated torque is the torque necessary for continuous motion. Anything larger, if you expose this mechanism or this mesh to anything larger than what you calculated for the Lewis formula, your mechanism is likely to fail. When there's a lot of factors involved, but at least if you reach this number and your mechanism is at the same value, then it won't break, at least with regards to bending. So you can proceed with your design. The next thing you want to look at is the surface strength. We can help with those calculations. Those calculations are a little bit more complex. But in short, if you find a failure in your surface, one of the things you can do to improve the surface is heat treatment, carburizing, and those are things that we in Designatronics are very good at providing, because we can calculate the teeth before carburizing, before the heat treatment. We can calculate those things before and after the treatment, which is very hard for people to do, because what happens is that once you send gears to get carburized or any type of heat treatment, these gears, especially if they're accurate, they grow. So if you don't know or anticipate what that will be, you'll have issues in your mesh, you'll have binding, interference, or even worse, your mechanism won't be salvageable, it won't work. So if you have any questions about gear strength, just let us know and we can help with those calculations. Next slide. The planetary gear trains, they offer very high ratios in a small amount of space. The way they do this is that they allow for multiple teeth to be at mesh at one point. You can see the diagram here. Instead of having a single mesh where only one tooth is in contact with another tooth, you'll have 4. So now you have 4 times the total load your mechanism can transmit. It'll also decrease the space. So one of the things here, one of the drawbacks is that the gear carrier must be highly accurate. And the shafts in the gear carrier must be true to the gear, total composite error. So if you have an AGMA 10, that gear carrier pin has to be the same concentricity as the spur gear requires total composite error. Otherwise, you'll have binding. Meaning you'll need to know what your backlash is, and you have to balance out not only your backlash, but you'll have to balance out the tolerance and what the best tolerances your machinist can hold for this. I think Designatronics can hold about, well, we can hold very tight tolerances on those gear carriers, but on a day-to-day, we're able to hold about 6/10, which is very hard for many manufacturers to achieve, and that's from day-to-day. We can achieve even a higher level accuracy on those, and we make these all the time. Again, just want to show the sample housing here. So if you have this internal gear for a planetary drive, again, the center axis is where you want to have the highest amount of accuracy when everything is in mesh. Next slide. As we spoke before, for manufacturing reasons, you'll need to know what your design requires. In this case, you'll need a relief or space for the shaping process to occur. So with shaping, the cutter moves in the vertical direction as the gear itself rotates. If you see the diagram on the right, you have external gears with a relief in the back. The internal gear below also has the relief in the back, and that is to allow the chips to fall into. So whenever you're making a design, you have to take into account the manufacturing method, especially if it's going to be hobbing, which we'll talk about next, or shaping, because this will determine some of your dimensions in the design. Next slide. Now, shaping can't always achieve the level, I'll go back, can't always achieve the level of accuracy that hobbing can do. So this is hobbing here. In hobbing, you have both the cutter and the gear rotating. Hobbing produces the best surface finish and produces the best accuracy versus cost scenario. It also can produce the highest AGMA quality. And again, it's made from the rotating hob and the rotating gear. Next slide. Again, for both of these manufacturing methods, you'll need a clearance. On the sample to the left, you can see how the clearance allowed the gear to be cut and not hit the wall on the right. The customer actually had this wall too much to the left, so his design had to be changed to allow for the hob to have enough clearance and not touch that wall. On the right, you have this spur gear, which did not have any clearance included in there. So it was impossible to manufacture. We had to get back to the customer and let them know that not only was this gear manufacturable by shaping only, but we needed to decrease the face width or the width of the gear teeth and allow for a relief for the shaping to occur. Now, in this case, you need to be at least below the root diameter of the gear and at least the width of the gear tooth itself to allow for the chips to fall into. Next slide. So there's a lot of errors we find with customers when they need gears. Sometimes they get a little bit confused as to either the name of certain features. So we just want to go over these few things here. So the testing radius itself includes the actual rotation error and tooth size. So this, if you can see the diagram here for the spur gear data. So the testing radius value, that includes the total composite error. So that gives you, if you're going to make a manufacturer gear or give us a gear specification, if you give us the testing radius, that includes the error and the tooth size all in one. So this gives us everything if you want to go this route. Now, whatever your mechanism is, you will need to have the axis of rotation be within the testing radius values. If you have that, then your gear mesh will work. There's a lot of mistakes from customers where they'll provide a very accurate measurement over wires measurement, but they think that the tooth thickness itself, just because it's accurate, it'll provide accuracy in the mesh, but that's not true. So the measurement over wires will just give you the tooth size itself. It won't give you the tooth size in relation to the axis rotation. That's what the testing radius does. So the measurement over wires will only give you the tooth thickness. As you can see in the diagram on the right, that's measurement over wires for even number of teeth and the odd number of teeth. So in this case, the total composite error is included separately, but again, it's including in the testing radius, as mentioned before. This is an example of an AGMA quality 13 gear, but all we need to generate gears is the number of teeth, the pressure angle, the diametral pitch, and the AGMA quality, and we can generate all the other information from that. But if you do need any modification or any modified part, it's best to give the testing radius as it includes everything all in one place. Next slide. We do provide gear tapes. So the axis of rotation error plus the tooth-to-tooth error, it's the total rotation error or total composite tolerance. Again, we offer 100% inspection for a tooth profile or complete gear tapes to prove accuracy. This is what the chart looks like here. Again, this will prove to you that the gears are made to the specification that you need if you want to go that length. And if you have a situation where you really need to know what the accuracy is on the gear and not just take it as AGMA 10 or AGMA 11, but you want to see what it is. This was used in a very high accuracy 3D printing application where the accuracy had to be known and the error recorded. Next slide. So a foolproof way to make sure that your gears will mesh is to add the total composite tolerance as a minimum to your center distance. The closer you are to this value, the more accurate you'll be to your gear mesh. So again, the tolerance is added to the housing where the bearings are mounted and where the gears will rotate. You can see the diagram to the left, how all these center distances have as a minimum, the total composite error added. So what this allows is as the gear rotates and that error occurs, there's a gap that accounts for this error. So let's say the center distance, the nominal center distance is 0.375. Where you want to be at is the minimum is 0.376, and your gears will mesh no problem. Here's a quick reference to all the AGMA qualities for further designs that you might have, in case you need to know what that value is.